Okay, so we have seen that we can approximate function f by its Taylor polynomial, right? So something like, let's change here k and a, right? So we have the nth derivative of f at a divided by n factorial times x minus a to the n, right? This is the approximation, plus, and then the remainder of this expression, right? We have seen that we can do this for some functions, right? Now the thing is, suppose that f can be infinitely differentiable in an interval containing a, right? So the question is, what happens if we take the limit? This expression is true for every k, right? Because if f can be infinitely differentiated, this is true for every k. Now, what happens if we take the limit when k goes to infinity of this? Well, this expression doesn't depend on k, so it's the same. And then we have the limit of this is the series, right, of the nth derivative at a divided by n factorial times x minus a to the n. And then we have the limit when x goes to infinity, when k goes to infinity, of the remainder of k of the polynomial k at a at x, right? Now the question is, if this goes to 0 as k goes to infinity, then we can express f as a series, right? This goes to 0, the limit of this is just a series, okay? And in this case, we call this thing is the Taylor series of the function, and there's an equivalence between these two things, okay? But the equivalence will only be true if the series is convergent, right? Because it can be the case, but that this doesn't converges. Sorry, this is not convergent. Okay, so how can we compute where this series is convergent? Well, this series is just a particular case of what we call power series, which are just series where the terms are powers of x, right? So it's just a coefficient a n multiplying x minus a, right? So this is a power series. And in the case of Taylor series, it just means that a sub n is just the nth derivative of n f at a divided by n factorial. Okay, that's what it means here. Now we can apply, where is this convergent? We can apply the root test, right? The root test to this, and it says that this is going to be convergent if the limit when n goes to infinity of the nth root of a sub n times x minus a to the n is smaller than 1. Okay, implies convergence, right? Now let's compute this, right? This is the limit when n goes to infinity of the nth root of a sub n times, and then the absolute value of x minus a, right? It has to be smaller than 1. Or in other words, you see that this will be dependent on the distance between our point x and a, right? Or in other words, this is equal to the difference between x and a, the distance between x and the point where I'm approximating the function has to be smaller than 1 divided by the limit when n goes to infinity of the nth root of a sub n. Okay. Now typically we call this rho. Okay. And so we call this the convergence radius. Okay. It gives a sense that, it's 1 over p over rho is the convergent radius, because this means that then x minus a has to be smaller than rho, okay, the convergence radius. And so our approximation our expression of f as a series will only be true if the distance between x and a is smaller than this convergent radius. Okay? So in other words, this series is going to be absolutely convergent in this interval, a minus rho, a plus rho. Okay? Remember that. Now there's another way of computing the convergence radius, because we know that this is also going to be equal to the this limit, the quotient, because of the quotient test, right? It's the same thing. Okay. Can we compute the convergence radius of some well-known series? Okay, let's see what happens with the exponential. Okay. So the exponential, if you remember, is if you take the polynomial of degree k, is just the nth derivative. Sorry, this is not this is just going to be 1. So this is x to the n divided by n factorial plus the remainder. Okay, at 0. Sorry, this is remainder k, right? And the remainder, if you remember, it's going to be the derivative, the kth derivative at the k plus 1 derivative, sorry. The k plus 1 derivative at some point c, right? And remember, we can write c as 0 times 1 minus theta plus x times theta, right? Or in other words, theta times x, where theta is in 0, 1, right? Divided by n plus 1 factorial times x minus a, in this case, which is 0, x to the n plus 1, right? Now the case is that the derivative of the exponential is always the same, so this is going to be e to the c, or in other words, e to the theta x times x to the n plus 1 divided by n plus 1 factorial, right? Now, what happens if we take the limit when n goes to infinity of this, right? So let's say the limit when, oh yeah, I mixed k and n, sorry. So this is k plus 1, k plus 1, k plus 1, k plus 1, right? The limit when k goes to infinity of the remainder, in this case, is going to be the limit when k goes to infinity of this e to the theta x times x plus, x to the k plus 1 divided by k plus 1 factorial. And so e to the theta x, theta is going to be 1 at most, so this is smaller than the limit when k goes to infinity of e to the x, because between 0 and 1, you know, the exponential is increasing function, so the maximum value you can take is e to the x, right? And then we have x to the n divided by, x to the k divided by k plus 1 factorial, right? But now, as you can see, x is just a number, okay? It's just a value. So these two things are going to be, how to say? Sorry, the exponential is going to be, wait a minute. The exponential is going to be a constant as regarded to this limit, right? And then this thing, x to the k keeps increasing, but k plus 1 factorial it's much increasing. It's increasing much faster, right? Because we know that n factorial is x to the n is negligible in comparison with n factorial, right? Because if you think about it, it doesn't matter how great x is. After some point, n becomes larger than x, and then you keep multiplying things that are greater and greater and greater than n, and things you're just multiplying x over and over again, right? So at some point this gets very small, so this limit is going to be 0. Okay, so the limit of this remainder is going to be 0. Okay, so in this case we know that the exponential will be able to be expressed like this. The limit, the sum from k from n equals 0 to infinity of x to the n divided by n factorial, right? Now the question is, where is this, what's the radius of convergence? Now again, we need to compute the limit when n goes to infinity of, for instance, we using the quotient test, a to the n plus 1 divided by a to the n. A to the n plus 1 is what? Is 1, yeah, sorry, it's x, wait a minute, x to the n plus 1 divided by n plus 1 factorial, all of this divided by x to the n times n factorial. Or in other words, this is the limit when n goes to infinity of x divided by n plus 1. And again, because x is constant, this limit is going to be 0. Okay? And we know that this limit is equal to 1 over rho, where rho is the radius of convergence. So that implies that rho is infinity. Okay? This series converges everywhere. Okay? It's convergent everywhere. Okay? So this approximation, well, no, sorry, not this approximation, this equality of the exponential and this series expression is true always. Okay, so you can actually think of these two things as being the same all the time, right?